Wait, how much for next week? Where are you going? She just, it would just be the
No.
You can't go in the fence area, it's like, you can't go on the field or anything. And so.
Sean's here, Braden's here, Cheyenne, Nikita, Zach, Zarita, Zane, Mason, AJ, James, Hannah, Jaden, April, Alyssa.
I don't know, but
I remember seeing them.
I remember seeing them.
Hunter, that way please. Okay. So the question, what number was it again? Was it 8?
8.
Okay, so we're covering number 8. Quick refresher on even and odd functions. An even function, an example of one at least, would be something like y equals x squared plus 1. And this, I'll give you the definition of an even function is that f of x and f of the opposite of x are the same value. So an even function, if you plug in a number, and then you plug in the opposite of that number to the function, you get the same exact y value for any x value you pick, okay? And so like in your table of values, for example, you might go, well, if you're doing a math problem and it says, is this function even or odd? A typical approach is to go, well, if I plug in 3, I get 10. And if I plug in -3, I also get 10. That's a big hint that it's an odd function. Sorry, an even function. Sorry. An odd function, a good example of that would be something like y equals x cubed. Okay, to establish that, you might be looking at pairs of points like, oh, 2 gets me 8, -2 gets me -8. So the definition of an odd function is that f of x is the opposite of f of the opposite of x. That was a little bit more of a tongue twister, I guess. Okay. So the question we're asking today is, say, let's just start with a simple one, the sine function. Let's look at the sine function. So we're going to eventually break this up into even and odd functions, but let's look at the sine function. So like a table of values, so as we make a table of values, I'm like, okay, what's a good number to plug in there?
0.
The problem with 0 is, what's the opposite of 0?
0.
0 again. So we'd like to get, just like over here, we'd like to get 2 different numbers that are distinct. 2 is tough because the sine of 2, I mean, you could look at it, the sine of 2 is an irrational number. Or okay, pi over 2, that's a good one. What's the sine of pi over 2? 1. What's the sine of the opposite? -1. Are there any questions on that? Okay, that's a pretty good hint that the sine function is odd. By the way, I mean, we know that, think geometrically, odd functions have origin symmetry, meaning the point 2,8 and the point -2,8. You know, if they're star-crossed lovers, they look at each other through the origin. Whereas the point 310 and -310 look at each other through the y-axis, right? So just looking at the sine graph, right? We graph this one. Just curious, do you see how just that visual kind of tells you it's an odd function? And ultimately, all this stuff's going to come back to the unit circle. So like in the unit circle, the idea we're talking about is like, we'll take some angle, you know, theta. Could be anything. That could be, it could be a really well-known angle, like pi over 4, but it could also be a less known like pi over 5, or it could even be a random, you know, it could be 1 radian. It could be 0.8 radians, right? But no matter what you picked for your angle, if you looked down here, what am I looking at now? negative theta. Is this making sense?
Yeah.
So consider, as you look at this, how do these two angles, how do their sines compare? How do their cosines compare? How do their tangents compare? So for example, does it make sense how, like in this case, the sine of theta and the sine of negative theta are opposite values? Is that making sense?
Yeah.
Okay, so long story short, sine is odd. This is a strong unit circle argument for why sine must be an odd function, okay? Let's do cosine next. Sorry, it might not be the most organized board ever, but look at the cosine function. I don't know if I need a table of values anymore, because once you have this, look at this guy's cosine value. And look at this guy's cosine value. What's going on there? They're the same. So the cosine of theta is equal to the cosine of negative theta. So therefore, this function must be even. Does the graph kind of show you its evenness? Cosine graph looks something like this. Right? Cosine looks, I mean, it's a nice perfect reflection over the y-axis. Cosine's an even function. Okay. Think about tangent. What do you guys think about tangent? Odd. Yep. So back to our circle, the tangent of theta would be positive, but in this particular case, the tangent of negative theta would be the same size number. It would be the same like magnitude of number, but it would be opposite. Okay. So that tells me that the tangent function is an odd function. And once again, does the graph give us a nice intuitive reason to suspect that it's odd? I would hope so. The graph looks a bit like a cubic, doesn't it? So when you graph a tangent graph, you can see that origin symmetry. All right. The last three are sort of an afterthought. We actually haven't even graphed them yet as a full exercise, and I might have touched on it really briefly. We will go over it in actual depth, but if this guy is odd, what other function would have to be odd? Secant, very good. So secant is the reciprocal of sine. So I might just do this in green, like right nearby, because so sine and secant are like best friends, right? They're reciprocals of each other. Okay. Do you understand that? And that's just because, take for example, I'll throw you one example here. So suppose this is your function. A little bit of review for you. Does anyone feel confident that they know the secant of pi over 6? Secant of pi over 6. Anyone? 2. Very good. How do we figure that out? We go, well, the sine of pi over 6 is 1/2, and the secant's reciprocal, so the reciprocal of 1/2 is 2. How about negative pi over 6? Well, the sine of negative pi over 6 is just negative 1/2, so the secant would be negative 2. Does that show you the oddness?
Isn't secant the cosine reciprocal?
Oh, thank you. Thank you. I got mixed up. Zarita, you get $1 million zillion.
He was testing.
Oh, I was just testing you. Thank you, AJ. I was testing you. So where were we? Yes, thank you. cosecant is an odd function. And this is true for. Make sense?
Yeah.
Okay, so then cosine, right? His reciprocal is secant. So maybe just right nearby here, we'll say, well, if the cosine function is even, then the secant function would also be. And if the tangent function is odd, what other function would have to be odd? Very good. Okay. Is also. So in the full breakdown here, how many of them were odd? 4. 4 of them were odd. So if sine is odd, sine's best buddy cosecant is odd, tangent is odd, and tangent's best buddy cotangent is odd. Even ones, there's 2 of them. There's cosine and his buddy secant. Okay? That'll help us when you're graphing. So like, we haven't graphed the secant function yet, right? But what's going to help us graph it is like, we know it's an even function. So it's going to exhibit the same type of symmetry as the cosine function, right? Here's a good question. Just looking ahead. What is this guy going to have at the x values where this guy has zeros? Asymptotes, very good. So this dude's going to have asymptotes at the same x values that this guy is equal to 0. And then when this guy equals 1, what does this guy equal? 1, because the reciprocal of 1 is 1. So with that in mind, that's actually enough to pretty much graph the function. If you know those 2 things, you can kind of maybe already visualize what it's going to look like. Okay, let's look at. We okay to move on? Are there any questions? Okay, let's look at the next one, 9. Take a second to read it, and hopefully it was written clearly enough that you know what it's asking you to do. Any of you guys, any Greek scholars in here know what that symbol is? That one symbol I don't think we've used it yet this year in this class.
You might have showed it as next class.
Yeah.
I don't remember.
It's anyone want to try to guess at what this symbol is called? Its name?
It starts with an A.
Maybe you're thinking of alpha, but it's
No.
phi,
No.
or some people pronounce it phi. It's just another Greek letter in the Greek alphabet. Just like pi and alpha and theta and gamma, all that stuff. Omicron, omega. Okay, so and they just use it a lot. To describe angles. Theta is the king. Theta is king of the angles. The other guys that get used for angles are phi, alpha, beta. Your fun fact of the day, your fun trivia fact of the day. There's a Greek letter named phi. Or phi. Oh, you know when we briefly mentioned it because they used that letter for the golden ratio. We did that problem about the golden ratio. But it certainly was an afterthought. Okay, so anyway. They use it in spherical coordinate systems. You guys ever heard of spherical coordinate systems?
No.
It's like a,
I think we also talked about that in physics once.
yeah, it's like a, it's really fascinating. It's so if you wanted to say where something was, like a point in space, so say you're in a box, it would make a lot of sense to use a rectangular coordinate system where you might say, well, let's call this point 0, 0, 0, and have an x, a y, and a z axis. And you can describe any point in space with a triplet of numbers of how, say this point over here. Okay, I have to go over this amount, and then up this amount. But then if you, and in a lot of applications, that's the best way to do it. But if you're in like more of a round system, like on a globe, for example, they end up going like, you do a spherical system, and so you talk about, well, you have like a radius, and then you've got like a theta, and then you've got like a phi. So you describe your position in terms of a radial value, your distance from the origin, and then two angular values. Just throwing it out there. That's another place where you'll see phi. There's also a cylindrical coordinate system where you use a radius, an angle, and then a height. Anyway, our Earth kind of uses a spherical coordinate system. Latitude and longitude.
Yeah.
Those are kind of like the theta and the phi. in a
Because we're
sense.
pretty much the same radius on the Earth unless you've wandered up into the
Exactly, yeah. You pretty much always have the same radius, so you don't bother to like specify that. Okay, sorry, where was I? This question is asking, where are, if you make a function, okay, there's your function. I wrote that down right?
Mhm.
No.
It's minus.
It's minus?
Oh, it
Thank
is
you.
minus.
Thank you.
Then you can say what?
So what do these three things do to a sine function? What does that guy do? Vertically stretches, exactly. Amplitude, does the amplitude. These two guys, this is where it gets a little weird, but this guy affects the period. This guy kind of shifty-wifty. He shifts it left and right, okay? Now, if there's no k there, then it's really simple. If there's no k, then it's just, whoa, he shifts it over that much. But when you throw the k in, that actually kind of makes it a lot more complicated. That's what this question is trying to do, is get you to see where is that, like, quote unquote, first zero going to be. So, how do you find zeros of like any function? What do you do? You plug in 0 here if you want the y-intercept. For the x-intercept, yeah. So recall the definition. The x-intercept is happening when y is 0. Right? Okay. So what's the first, if you solve this equation, what's the first thing you would do?
Divide by.
Oh, let me clarify something. What are we solving for? No, okay.
Great question.
X. So think about an x-intercept, guys. An x-intercept on a graph is like here, right? So just for example. So that point has an x value and the y value is 0. So in general, when you want an x-intercept, you set y equal to 0, and you solve for what x value makes that happen. What x value makes the function equal 0. Are there any questions on that? Okay, so we're solving for this guy. The big question is, what does x have to be to make this true? Here's another question. How many x values are going to do it? Huh?
Infinite?
An infinite amount. Right? Because look at a sine function. What do sine functions do?
Infinitely do the work.
Right? Now, a lot of times when you're analyzing them by hand, you just maybe look at one period or 2 periods. But if you say graph it on Desmos and zoom out, you'll see it just goes forever. So, of course, that's just it's a plain Jane y equals sine of x. This guy's different. Okay. So unit circle. I hope some of these questions are maybe clarifying for you. Why do they love the unit circle so much? Well, when answering almost any question involving trig, there's a large family of questions you might ask involving trigonometry where you come back to the root. The root is where on the unit circle do we get sine values of 0? 0, pi, 2 pi, 3 pi, 4 pi. So we'd have a whole family of statements. Things like, well, the sine of 0 is 0, and the sine of pi is 0, and the sine of 2 pi is 0, and the sine of 3 pi is 0. Okay, I'll stop, but you get the idea, right? So does this A matter?
No.
A doesn't matter. A canceling cancels, which I hope agrees with your right understanding that when you stretch a function, do you affect the zeros?
No.
Nope. Okay, so what's the first thing I'm gonna set this thing equal to? 0. What's the next thing I'm gonna set it equal to? Then, get the idea? So you could say kx minus phi could maybe equal 0. That's the first possibility. That makes sense if I point to both of them. Like, if this thing is the same value as this thing, it'll equal 0. And the answer to that would be x equals
5
phi over k is the first one. So that's the first. So just for example, if k was a 3 and phi was a 2, the first x-intercept would happen at 2/3. Okay. All right, next one. Kx minus 5 could also have equaled pi. That would get us an x value of same thing, but you'd add the phi divided by k. So you get phi plus pi over k. What if you had kx minus phi equal 2 pi? Very good. And so this is a pretty nice way of writing the answer dot, dot, dot. We can see the pattern, hopefully. If you wanted to just generalize this into one statement, you could say something like, well, let's see, maybe one of you guys can.
5 plus or minus I n over k.
Very good. I'm not going to use the plus or minus. It's not like it's bad or anything, but if we just say n can be an integer, then we take care of the negatives. So then you say, well, phi plus any multiple of pi over k, and then just clarify that n is any member of the integer family.
Needs.
Huh?
Needs.
Needs. Okay. $26. All right, we can cover the thing I wanted to cover. So 10 I want to save for you. You are free to figure out. If you guys get stumped on it, I can try to give you some extra hints and stuff, but it's the same idea as this. You're going to try to identify same kind of setup. Is like, what does this have to equal in order to get the peaks and valleys on a sine graph? And then the A and the B are going to be involved. Okay. Last thing is about identities. Does the bell ring at 21? We'll do the identities one. We're all done.